Hello and welcome to the demo 2 of the Getting Started with µRTE. My name is Thomas Barth and I'm the creator of µRTE. It is assumed that you already have seen the introduction of µRTE and the demo 1 because we will make use of what was said in there. In this video, I will use the plugin version of µRTE to model a basic system based on the template that was presented in Demo 1. So let's build the hello world of embedded systems, which is a blinking LED. Before we can build the actual application, we first need to make sure that we have resources to run the application on. So the very first thing I do is to create a task. So for this particular task, I'll give a name, maybe a description, and I associate it with a core. Also, what we can see in here, what is missing is a stack. So I'll quickly create a stack for this task. I make sure that the output section is associated with memory, and then I can reference the stack from the task. So please refer to the integration guide of µRTE on how to integrate now the generated task activation engine onto your OS task. This is not covered in this video. And a very good approach to test if we're still on track is to check the model consistency. Okay, so for now everything seems to be okay, so we can start to model our application. For this, I will now use the graphical representation. In the application area, I will create a new diagram, which I'll call signal flow LED. So this is now the top level representation of the software we want to build. I'll create a new software component here. So a software component is nothing else than a code file. So call this one LED, contains, and I'll give a file name with which that file will be generated. So I can decide if I want to generate that file too, or if I want to reference or use this software component as a reference to reuse functions which are already present somewhere in my system. So I can decide if I want to generate it. And for now, if I don't give any directions on where this should be generated, then this will be generated into the default folder as it was configured for this project. Okay, now that we have the LED software component in place, we can double click it and create a graphical representation of the inside of the software component. You can also see in the tree now, this was our top level representation, and now we are within the software component and have a diagram here. The idea is that you can create as many diagrams as you want, and each diagram can show different things. So for example, in this system now we only have one LED software, one functionality, which is this LED. But if we would have multiple, then you can decide what should be shown in those diagrams. So for example, here I just hit the software component, and I can bring it back through this context menu. Now within the LED, the first thing I do is I'll create a runnable, which I call run LED, and this runnable now shall be responsible to control our LED. Then a brief description. And I already get an error here because this runnable is not associated with any system state. So the system state selection here defines in which system states the runnable shall be active in, and as we only have one system state now in this model, I select that system state. Now that I have my runnable, I can create and trigger import for this runnable, which I maybe call tick, because I already know that I want to associate this trigger port with a cyclic event, so with a tick, and I assign the task in which the runnable shall be executed. Now I associate a cyclic event with this trigger port, and in here maybe let's call this cyclic event LED timer. I can define a cycle time. In that case, let's say 100 milliseconds, and create this timer. And now this runnable will be called every 100 milliseconds. Now let's maybe already check if we are on track. So we check the consistency, and then maybe already let's generate the code to see what has changed. By default, the software components are generated into source ASW SWC. There's our new file, and we can see this is the runnable as we have it modeled. And we can see also that the trigger port, which will later on be passed by the task activation engine, now contains the trigger port we have defined. All right, so the next step will be to associate the runnable with an hardware interface through which the LED can be controlled. And in µRTE, hardware abstraction usually is realized with signals. I quickly want to give an overview about what an signal is. What you can see in this picture is not the entire feature set of signals, but a simplification. At the heart of the signal, there's the payload along with meta information such as the signal age, its validity, or its checksum. And whenever data shall be written into the signal, it first has to pass a verification method, which can be defined by the user. So every time you generate a new signal, it will nag that you first have to provide some code for the verification. If the sender, so if a runnable wants to write a signal, it can use the set method if it already has the correct data type, which suits the payload. Otherwise, alternative data types can be defined, and in that case this set method accepts the data type as it was defined as an alternative data type, and then the user has to provide scalar functions, or the body for those scalar functions will be automatically generated, in which the data type conversion takes place. Signals can be associated with in and out drivers, with one in driver or multiple out drivers. So if the user now wants to, for example, wants to get new data from hardware, an in driver can be defined for this signal, and this driver then performs the actual hardware access either directly or through an underlying hardware. And those methods here, the difference for that is pull port in is the call for a synchronous driver, request port in, and then later on push port in are the interface for asynchronous driver calls. In order to read data from a signal, so let's first focus on the runnable point of view, the application point of view. The get method can be used. This will load the payload, but also the get method will check the validity, and it is very critical to always check the return value of those operations. Similar to the input side, we can also define alternative output types, and if such a method is called with an alternative output type, then we have so-called out scalars generated, which will translate the payload type into the data type as it was defined in the model. Moreover, we can also associate out drivers with a signal. In that case, so the payload will be passed to a driver, and here the push port out method is valid for synchronous and asynchronous calls. One of the most important configurations of signals is if a signal shall be local or global. Global signals are stored in global RAM, and all the runnables access the same data object. If the signal gets modified, only a notification is sent to the tasks, which then in turn will activate the runnables. While with local signals, each task has an own copy on its own stack, and if such a signal gets modified, then the notification about the signal change along with a deep copy of the signals is sent to all tasks which also have an own copy of that signal, and this has the effect that there's some kind of inbuilt queuing which will make sure that the signal payload is associated with the event, because if you have a global signal, then there might be a case that the signal has changed in the meantime before a runnable can process it. So let's add a signal to our runnable through which we want to control the LED via a driver function. So we have our runnable run LED. I'll call this port out, and maybe also the software component shall be called out. I want to create a new signal because in my system right now I do not have any suitable signals. So my personal naming convention is to call this HWO, hardware out LED. And for now, there's not too much I can configure, and I leave it as it is for the time being. Also, what can be seen now is that this data output port, which we have just created, is now also visible on the outside of the software component. Next, I will create a driver function through which we want to control the LED. I will create this one in the same software component as the runnable. So in that case, this is now an out driver. I'll give it the name drive LED, and I will associate it with the GPIO I later on want to control. If I now would generate that system, I would get two type definitions, one for this driver and one for the signal, because for both I have not defined a data type so far. So in that case, if you don't have an explicit data type, and type definition is automatically generated, which has to be provided or to be filled by the user. In order to keep it simple, I will create a new data type, which I call LED state type, it is an atomic data type because it will be at the end of the day just a single byte or a single word in the worst case. It is not primitive, so it actually needs to be referenced or included wherever it is used. The initial value for it, if not defined otherwise, is the literal false, and we do not need a type def path because we want this to be an internal type of µRTE. What has to be done next is to simply associate the driver as well as our signal with the newly defined data type. Now let's simply generate the code and see what has been changed. Oh, and there's something missing. The data signal now needs to be associated with our newly created driver. So we simply generate the code again. A simple way to check what is missing in the code is to simply build the project, because for all the missing adjustments, µRTE will generate those error symbols in here, those error messages. So for example, in this particular case, there is no type definition for our newly created LED state type. So we'll simply give it a bool. Also, what is missing is the validation code for our newly created hardware out LED signal. And because this is a binary value and we have not defined any specific rules here, we simply say validation not possible. Okay, so let's try again if we can build it. Okay, we're good. Now let's have a look at our software component, what has changed in here. So we have our new driver in here. It gets the payload, which shall be written to hardware as a parameter, and it has to return information if this operation succeeded or not. In here, now you could do a direct register address and directly access the hardware, or also what can be done in here is to use already present drivers in your base software, simply to have this as a wrapper and interface between µRTE and the base system. If includes or something like that for those driver calls is required, there are user code fields for includes or for own functionalities up here. Also, the runnable has changed a little bit. We now have an additional parameter which represents the outgoing data signal. We want to make an LED blink, so we need to perform the following steps. We need to read the current state of the LED. We need to write the inverted state into the signal. And we need to write the inverted or the new value of the signal to hardware. If we want to read the current state, so if we want to read from data signals, we need to provide local buffers in which the signal payload is stored. And it is highly recommended to use this data type of the signal, because this internally will map to the data type with which the signal is associated. So if at some point the data type of a signal changes, then still this is at least to this point valid. Now let's perform a read operation on the signal. It is highly recommended to always check the return value of those signal operations, because, for example, in that case, the get operation might fail because the signal is not valid, and in this case, for example, this buffer would be not initialized. So you always have to make sure that the operation succeeded before you continue using the data from which you think that you have just read it. Similar with the set operation. Also here we should always check the result, but I will skip this here simply for simplicity in this demo. And the second parameter here theoretically could be used to provide a buffer in which the validation result is stored to ease error handling, but again, this is skipped. And now the last thing to do is to perform a push port out. Again, here we can provide a buffer in which the driver result is stored, but we do not want this, and we'll simply skip this part. So we save everything and we build our project and we're good. Don't be shy to look into the logic of the signals to understand what they are doing. So for example, in here in this push port out, we can see that first the validity of the signal is checked again, and then simply this driver call, as we have it defined in here, is performed, the result is buffered, and so forth. Also, what might be interesting here to know is that in this signals folder, those files down here, they have the implement or the code of the signal itself, while everything which can be adjusted by the user is located here in this config folder. Also, we can simplify our code a little bit in here, because there is a set and push port out method available with which we can perform those two steps in once. If we now would have provided a driver function here, we already would have our blinking LED. What also can be seen is that the memory configuration of our LED task now contains the access rights to access the underlying hardware and to perform the driver operation. Alright, so now that we have our blinking LED, let's clean up a little bit. And let's focus on the logical function model and the requirements model. I will now create the logical function model for our blinking LED. I'll first start with a new diagram for that. In which I will create the logical components out of which my system consists. So in this easy example, I might want to have a logical function block controller, for example, which in terms of this logical function model is a service. And I might want to have my LED, which is the output. And now I can simply connect those two blocks with a signal again. And that's basically it for this graphical representation. But I want to add a little more information. So for example, what I also can add is the technical function. And the technical function as already introduced, is a description of a system functionality. And the idea of that is I'll map this technical function to the actual implementation of a functionality of the system, and then I can, with the help of the technical function, decide if, for example, within the context of a task, if there are multiple technical functions. Also, what I can do is from the logical function model with our newly created blocks, I can reference to this technical function. So if this technical function now is our blinking LED, I can map this technical function now to the software functions which execute this this technical functionality, but also the hardware it is associated is. There is no rule for now, for example, for the hardware, if now the core or the RAM and so forth should be also associated with this technical function, because this depends on your system where you want to draw the line. Because if you now would associate everything with this technical function, then very quickly this becomes very messy, but it might be necessary in some cases. So it depends on the system and the required safety, the applicable standards, and so forth. However, now in this case, for our simple example, we can now also reference from the logical function layer, or from those logical function blocks, to the technical function, and the technical function in turn will now map to the actual implementation. For the requirements layer, I already have an empty diagram in here, and before we can create any elements here, we first need to create a package in which those elements will be contained. So this package now is related to LEDs, or to this LED functionality. However, how you want to organize those requirement layer elements is up to you. Maybe let's start with in simple abstract requirement here, which is something like an LED shall blink, can give some description and so forth here. The creation date, the format of the creation date is the Java datetime format. You have to stick to this particular format because this will allow the tool to do calculations and so forth with the creation date. So this is not a string, but a real datetime. And then later on, or down here, you can define some characteristics or more attributes of this requirement. And once we have created the requirement, we can also map it to the implementation. So what I'll want to show here is that I can, for example, reference the runnable in which this functionality or this requirement now is implemented. And if I generate the code and look into the project again, make sure that it's refreshed so that we have the latest code, then for this runnable we can see the requirement. If I now want to refine this requirement a little more and to say something like let's call this, yeah, Then I can create a refining relation. So this is blue one, the blue relation. And then I can, in this case, now map this requirement, for example, to the timer event. You should really think about, if you create requirements, where does it make sense to map those requirements to. This is not like a technical function where you try to cover everything which is somehow associated with this requirement, but where actually something has to be adjusted or to be done. Yeah, so for example, as it is in here, an LED shall blink. This is implemented within software, and it is implemented within this particular runnable. So there's the logic in there. Of course, the signal transporting the data from the runnable to the LED, or the hardware building the connection to the outside world, are related, but this is not the point where something is actually adjusted or done. So you have to be a little bit careful with that one, because otherwise you will create a lot of dependencies which are hard to manage over time, and because the entire model will become very complex. All right, that's the end for this demo. In the next demos, we will look at the other example projects and what has been done there, and simply to highlight a little bit the features µRTE also has implemented. That's it so far from my side. Have a nice day.